It's day 23 of Advent of Code 2024, and let's get started solving it. So today we're organizing a LAN party where we have a list of connections between pairs of computers, and we need to find sets of free computers where each computer is connected to each other. So for example, in the sample input here, there are 12 such sets. And we are looking for our chief historian, who is working on a computer which starts with T. So we only consider sets of free computers which contain a computer of which name starts with T, and then we need to find the number of such free interconnected computers, which contains at least one computer with name of that starts with T. So that's our task. So I will take the sample input and let's try to solve it. So here's the sample input, and let's first read. So edges. So await input reader lines. So this will read all our edges, and now we will have a graph. So we'll have a private. So we could have a dictionary of a string pointing to the hash set string graph. So this will contain our graph, and we will be adding, for each pair, we'll be adding the vertex itself and the edges it is connected to. And I will also have a hash set of string vertices. So this kind of adjacency graph. So for each edges, if we will split it, so our neighbors, edge split by its I think yes dash, so dash. So for each neighbor, if it doesn't contain the neighbor yet, we will add it, and we'll also check if not vertices contains neighbor, we'll add that as well. So we're adding just empty entries if necessary, and then we do graph neighbors 0, graph 1 neighbors 0. So I basically add for both sides, we add that edge as neighbors of each other. And then, so we now we need to find all free or sets of free which are interconnected. So let's do triangles with T. So it's going to be like triangles. So we will have a method that will be searching for triangles with the vertex of which starts with T. So that's going to be list of string arrays. So get triangles with T, and then what we will be doing here is for each vertex in vertices where B starts with T character. So for each that starts with T, we'll do second vertex, vertices. He starts with, well, that can be anything, right? So each vertex for each third vertex, vertices. So now we have 3 vertices, and then we check if each is connected to the others. So if graph vertex contains second vertex and graph second vertex contains third vertex and third vertex contains vertex, so each needs to be connected to the others. And if that is the case, then we add it to a list of results. So results, we will string, and we will do, or we can have, or actually we can build it up as a string together. So we can do vertex order by E and do string join. So we kind of join the vertices with a comma, for example, and then we add it to the hash set of results. So this will be unique. This way we don't accidentally create some kind of duplicate. And then we return results. So this is the, all right. So hash set is fine. So we return the hash set of results. That should be it. So now we have all the triangles and return the number of triangles that we found. So let's try to see if that works for the sample input. It's 7, so that's 7 sets. Yes, that's okay. So that fits the sample example. And now let's see if that works with the big input, because that's much larger, of course. So we will see if that is the case. So 1154. That is correct. Okay, so we have the first part solved. Now on to the second part. So in the second part, we are looking for the largest set of computers that are all connected to each other. Okay. Yeah, so given that we already have all the triangles, we can then try to make larger sets that are all interconnected from those. And because the number of interconnected sets will be getting smaller and smaller, it should be technically not as time complex as possible. Not that time complex, I think. So So let's see how do we do that? Could okay, let's see. We can have a hash set instead of string of a single string. So we'll do hash set and hash set string. So this will be our list of hash set. But we want to keep it unique as well. So let's see. This is actually fine as long as we kind of break it down afterwards. So I'm trying to figure out how to we have the components, and we want to find. Let's see. Let's see. Find components. So given the find largest component, find largest set, given a list of triangles. So here we will get the individual triangles. So first I will take the sorted vertices. So vertices ordered by list to array. So we'll have them sorted by name. So that's the first thing. Now we'll have a largest set. Or we actually care about just the set. Okay, the whole set. So we need the set as a string. So now we will be going through all our existing triangles and try to expand them with another vertex, which will make it larger, which will make that set larger. So so far current sets will be triangles. Select, split them by a comma, and get that as. So there's going to be a hash set, array of hash sets. So those will be the unique triangles. So and while current so we'll be doing the following: do new sets count not equal to 0. And we'll have some kind of new sets, which will be a new list of sets. So let's do a toList here as well. And we will be trying to expand and create a new set of lists, a new list of sets, which will have one larger size than what we have currently. So for each current set in current sets, we will be looking to find expansion that's possible. So for each vertex in sorted vertices. So if the current set that we are looking to doesn't contain the vertex, we will try to expand it to see if it is connected to everything that's there already. So if it doesn't contain the vertex that we're trying to add, we will check if it's connected to everything. So if current set all, yes, exactly. So if the current set, if all vertices in the current set contain the vertex, we will create a new set, which will be a copy of the current set, but with also the additional one vertex. So that's this. And we add it to the set of new sets. And finally, we will continue. So this will be creating a new set of sets. And so let's see. Set news. So we start with this. So we set the current new sets to current sets. Now, at the beginning of the loop, we will set the current set as new sets. It's a little bit confusing to write this way. I see. Well, but it works. So initially we will set new sets as the current sets. Then we set current sets as new sets. We clear the new sets and we add the new sets there. And if we encounter the end where we basically find that we no longer found any additional new sets, then we found the maximum size. So we can take just the first set from current sets first, and then we kind of generate the string that we are looking for. So we take all the names and sort them by name. So return first set select order by we select v. Well, it's actually done. So we can just do string join and join it like this. Yeah, so that should be it, hopefully. And actually, we don't have the rule of starting with t anymore. So we actually will do all the vertices completely. So get triangles. Okay, so that should be it. If I didn't miss something crucial, hopefully it will work. So we'll see. So test data. So recap. Okay, so it seems to work for the test input. So we'll see if it's efficient with the large input as well. Taking its time. So let's see how far we got in the size of the sets. So current sets. Oh, that is growing fast. So what is the issue here? We have a lot of sets there of size 5. I see, we have a lot of copies, I guess. I see, we might have a lot of copies in there. Yeah, because we will be creating the same set of multiple times. I'm guessing. So let's do it like this. We'll just use a string. And keep the sets as strings so we can easily hash them and see if they are duplicates or not. So we will take this as a string, hash set string. So this is the new set, and then we will be doing so we'll be this is in set, we'll split it by comma, and so if since all contain the vertex that we are adding, then we get the new set, which will be set at append vertex, and then we order by name, and then we string join again. It's not the most efficient solution, but it's allows us to make sure that we don't have any duplicates there, which should help with the performance, because otherwise we are just enumerating a lot of things multiple times, which is inefficient. So with this data, okay, so we have some problem there. How did we get this weird thing there? That is not okay. That is not okay. So we somehow are putting there something that doesn't make any sense. Oh, right. Currents first set. We already like return directly what we have there. That's one thing. But still not great. Okay. Okay, so that works. With the input file. Okay, so it's so the current sets are, there's still a lot of sets that are not processed. Yeah, let's run it. Let's let it go. And this is the result. Okay. We'll see what happens. Okay, it's correct. Okay, so it took a while to run. Actually, what is the runtime for the whole thing without breaking? Yeah, so 7 seconds. It's not very efficient, but it works. So overall, it is a solution that can be used. If we were to use something more efficient than just building up strings, we could do some hashing or some hashing of IDs of the vertices or something like that. Maybe it would be more efficient than this. But as it works, I think it's okay to keep it like this at least, because it still finds the solution, even though it takes a little bit more time. So yeah, we are done with solution for day 23. And there is just 2 more days left. So I will see you in the next videos, and also tune in for the ChatGPT solving this problem video. So see you there.